Hey everyone, welcome back, and let's write some more neat code today. So today let's solve minimum cost for tickets. We've solved this one before, but I think last time I didn't explain the bottom-up solution, so that is what I'm going to do today along with the top-down solution. And I guess I kind of just spoiled that this is a dynamic programming problem, but I'm actually going to explain why this is a dynamic programming problem and why it's not a greedy problem. And I think that's very important. The way this problem is worded, for me, just doesn't really make a lot of sense. I'll explain it to you quickly. Suppose we're given an array like this. These represent days, and we're guaranteed that all the values in this array are going to be from 1 through 365, and there's not going to be any duplicates, so we can assume that the size of this array, we'll refer to it as n, but it's going to be bounded by 365. We're also given an array of costs. So this time it is 2, 7, and 15. And so the way this problem is worded, they say we want to travel on every single one of these days. So I want to travel on day 1. I have 3 choices. I can buy a 1-day pass for $2 or whatever. I can buy a 7-day pass for $7 in this case, and I can buy a 30-day pass for $15. We want to know what is the minimum total cost it would take for us to travel on every single one of these days. For me to explain what they mean by that, I'll just quickly go through the example. So, for example, if we buy a ticket for 1 day for $2, we'll travel on this day, and then we're going to buy a 7-day ticket for $7, which is going to allow us to travel for 7 consecutive days. What that means is we'll be traveling from day 4 all the way up to, I guess, 4 plus 7 is 11, but we don't include day 11. So if we buy a 7-day pass, it means we can travel on day 4, 5, 6, 7, 8, 9, and 10, but not actually including day 11. We travel 7 consecutive days. So if we do that, you can see we'll be able to cover this range of days over here. We can't include the 20 for reasons I just talked about, because we can only do it for 7 consecutive days. We can't save a day. Even though this range here is of length 4, we can't extend it any further. So we are forced to buy another 1-day pass for this day. And so if you total it up, we bought 2 of these, so that's 2 plus 2, and we bought 1 of these, that's 7, so we had $11 total spent. The alternative would have actually been, in this case, to buy a 30-day pass. If we did that, we would have been able to travel all of these days with just a single pass, but it would have been $15, which is obviously more than 11. So that is the solution. Now, again, like the whole concept of traveling for me, it just doesn't really make a lot of sense. I kind of like to more think of this problem as like, these are like the days you need electricity and these are like the options you have. But anyways, I won't really go into that. You can think about the problem however you need to, however it's most simple for you. So can we be greedy with this problem? Because otherwise, there is a very obvious brute force approach where we literally choose every time we're given a decision. We have 3 different choices: buy the $1, $7, or 7-day, 30-day pass with these associated costs. So it'll kind of be like 3-branch recursion. So there probably is a brute force way. Before we get into that, why can't we be greedy? Well, how would you even be greedy in this case? Well, you might say, let me just pick the longest pass. And for all we know, this range could extend very, very long. Assume maybe it goes up to 100 or 200 or something else. I have some choices. I can pick the 30-day pass, and it says it'll cover all the way up until here. It'll be $15. So I want to be greedy, and I just want to try to go as far as I possibly can, but maybe there's another way. The alternative would be to do 7-day passes. Okay, well, with one 7-day pass, I can cover all of this. And then I could do another 7-day pass for this day. Well, I can't extend that 7-day pass all the way here, so then maybe I'll buy another 7-day pass. Okay, well, that would have been a cost of 21. And so, believe it or not, I think if we were actually given a costs array of length 2 and we only had 2 choices to make every time, I actually think you could be greedy with this problem. Correct me if I'm wrong, if somebody smarter than me has thought about this a little bit more. This is just kind of off the top of my head. Obviously, I didn't code up the greedy solution, but if we only had two choices, we actually could be greedy because you can literally just compare. Well, with the 30-day pass, I could get that far with a cost of 15, or I could do the 7-day passes with a cost of 21. I think it gets more complicated when you try to do a combination of both. So maybe we actually can't be greedy. I'm kind of confident that if we actually had these passes where we either choose a subarray of length 1 or we choose like up to length 7, I think we could probably be greedy with that approach, but you can see obviously why you can't be greedy when you have 3 choices, because I just showed you this way, but there's also the other way where we just choose a bunch of 1-day passes like this, and that would have totaled up to like 12, but it gets more complicated when you start doing a combination of them. So we could have done the 1-day pass here and then 7-day here and then another 1-day here. We could have also done it this way, 7-day pass, 1-day pass, 1-day pass. It's going to be hard to find the minimum unless you actually try all the different possibilities. So now we are kind of forced to go down the brute force solution. So now what is that 3-branch recursion going to look like? It's not going to be too difficult, but there are some differences. So obviously we know we have to keep track of like the index that we're at, the position that we're at, but that actually doesn't tell us the current day. So for example, I'm saying we'll start at index 0, which is in this case, day 1. It could have been something different. It could have been like day 10, who knows? But we have 3 choices. If I pick the ticket of duration 1, it'll give me a cost of 2. And so in that case, it's pretty straightforward. You're probably always going to increment the index by 1 because we can just go to the next day that we want to travel. But with the 7-day pass, it's less straightforward. We can't actually say increment it by 7. We can't say go to index 7 because in this case, index 7 is out of bounds. And we definitely can't reach this day with a 7-day pass. So we can try to loop. So this is what we're going to say. I'm on day 1, which is day at index I. I picked the 7-day pass, which coincidentally has a cost of 7 as well. So I'm going to take the duration of that and add it here. So that's the duration. So in this case, that would be 1 plus 7, which is going to be the value 8. So what I want to say is keep incrementing my index I until we reach this day or we exceed it. So basically, while let's say day at index j, my current index is less than this term, I'm going to keep incrementing j. I'm going to keep incrementing it by 1. And so in this case, that condition will stop once we get here to this position, which happens to be, I think, index 1, 2, 3, 4. So that branch will take us to index 4. The other one, day 30, it would end up taking us out of bounds. That's how you know that we're done. So that's actually the base case. So I believe here would be a 6, and then this will end up returning 0. So these are the subproblems of our recursion. The base case was 0 because we're saying that with an empty subarray, the cost of traveling on all of those days is going to be 0. But we know that on this path, we did purchase a $15 ticket for 30 days. And so we would take the return value of this and add it with 30 plus the return value. This is not the solution, so I'll just cross it out for now. And so that's pretty much how the recursion is going to work. I guess I'll draw out one of these paths just to show it to you. So here, again, we'll have the choices. I'm not going to choose the 30-day choice because that's not going to lead us to the solution. I don't want to make this too messy, but we will have the choice of picking a 1-day pass from index 4, where here, that would bring us to be at index 5. So we'll be there, index 5. Or we could pick the 7-day pass, which would also take us to index 5. So now you can see why this is going to be the better path. And just to make it clear, this is where we spent $1. This was where we spent $7. This was $1, and this was $7. Here, we would still have those two choices. We could go to index 6 two different ways, but this is not going to be the solution path. This is because now, if we just do another 1-day pass, we will be at index 6, which is out of bounds. And we only needed a 1-day pass to do that, which costs not $1. I'm really sorry. It's $2. Let me just redraw these. That's $2. So now the way this recursion is going to work is among all of these paths, we just want to minimize what the result was. So from this guy's perspective, we will take 4 rather than $7. And then from this guy's perspective, we will take this path rather than this path, which was $30. This path was only 2 plus 2 plus 7, which is 11. So we got the minimum. And the fantastic thing about this is we're only keeping track of a single parameter I, so it's very easy to cache this solution. Caching is called memoization, the way I'm going to do it with dynamic programming. And it's pretty easy to add that step to this. I'll show you how to do it in the code. In terms of time complexity, when we look at the code, I think it'll be clear that this is going to be a linear time solution, because even though we are going to have an inner loop, each of those loops is only going to end up iterating up to 30 or 7 or a single time. And all of these terms are technically constant. Even n technically is constant in this problem because the length of the input isn't going to be bigger than 365. So I'm going to write an inner function. I'm going to call it DFS, and then we're going to do caching to it. You could call it backtrack or something else. Doesn't matter. But the main base case is when we go out of bounds, when we reach length is exactly out of bounds. So in that case, we'll just go ahead and return 0. Otherwise, we want to do the recursion. We want to do 3 different steps. And I'm just going to do a loop for that. And let me just show you a nice little technique in Python we can do, because for each cost, this tells us the cost of each ticket. There are 3 different ones of them. They are consecutive. So the first one is going to be a 1-day pass. Next is going to be a 7-day pass. Next is going to be a 30-day pass. So we kind of want to map each to that. I could create a hash map. If you're using a different language, that's probably what you should do. Maybe call it C or something, and then you could say 1 maps to this cost, 7 maps to this cost, and you could do the same thing for the 30-day pass. I'm actually not going to do that, because Python, you can do something like this, where we take this array and zip it like this, costs, and then have this second array here as well. So what this does is now I can iterate over this and unpack the pair. So the first value is going to be the cost, and the second value is going to be the duration of that. So let me be a bit more descriptive. Cost duration in that. So basically it's going to combine these 2 arrays and make it like an array of pairs. And so that's very convenient for us. And now I want to take my I pointer and sort of advance it. So I'm going to say j is equal to I just to create a copy of it. And then I'm going to say while that pointer is less than days, we definitely don't want it to go out of bounds. And that formula I was talking about, where the current day that we're looking at is less than the day that we started at, days of I, plus the current duration. So there's that. So while that's the case, keep incrementing j. As soon as you're done with that, then we are at the day that we want to be. So then we can call DFS on j. And the current cost of that will be added to the return value of the subproblem. So cost plus the cost of the subproblem. And this is going to be our result. So I'll call that here. We're trying to minimize this value. So I'm actually going to declare the result over here. I'll set it to a really big value like infinity, so that now here we can say min of result and that. And then that's what we end up returning down here. A couple things I want to mention. We declared j inside of the loop over here, so it's always going to start at I. But since we're going through these consecutively, like since day 7 is always going to be further than the previous one, day 30 is always going to be greater than the previous 2, I could actually move this guy and put it over here so that we kind of reduce a tiny bit of the repeated work. But again, since this is constant, like this inner loop here is only going to execute up to 30 times, probably less than that. And this loop is only going to execute like 3 times. So that's why this stuff is technically constant. And that's why we can add caching to make it more efficient. I'm going to declare a hash map up here like that. And then so I'm going to add another base case here. If I is in DP, that means we already solved the current subproblem. We can just return the value of it. If we haven't, we will compute the result of the subproblem, throw it in the cache just like that, and then return. If you want to reduce this by a single line, you could do this, change this to dp of I, and change this to dp of I, and then get rid of this. and then change this to dp of I as well. And then you can call the DFS like this, return DFS starting from 0. There's one more optimization you can make here. We can see that if I is equal to this, we want to return 0. Couldn't we just throw that in the cache as well and say if I were to be length of days, the return value is 0. And then we can get rid of this if statement, and that will be handled by the cache anyway. So just some very minor optimizations. I'll run this for you now. And of course, I forgot to change this result, so that's also a dp of I. Now you can see that the solution does work, and translating it to a bottom-up solution is actually very easy in my opinion. I'll quickly draw it out, but in my opinion, you can actually just get to the bottom-up solution just from this code itself. So the idea behind the bottom-up solution is very similar to the top-down solution. It's just the order that we're solving the problems in. So previously, we're trying to solve this problem. We want to know from the beginning, if we're traveling on all of these days, what's the minimum cost? And then when we get to this here, index 4, we're asking, okay, for this sub-problem, what is the minimum cost for that? And then we can add that to what we had already. Well, we could solve these problems in reverse order. That's what bottom up kind of means. And so that's exactly what I'm going to do. So what I'm going to do is create another array, a sort of copy, well, not a copy, but of same size as this. And so what each of these is going to represent is the same thing that we had in our cache. For example, when we're here, this means what's the minimum cost to travel on all of these days? Well, there's just a single day, so probably the 1 day pass will be sufficient. So I could just say the cost is going to be 2. And that's good. So the rest of this can pretty much just be solved with the exact same formula if we just iterate in reverse order. You could technically have iterated from left to right. There's nothing wrong with that because if you think about it, the problem is symmetrical in the sense that we want to just travel on all of these days. Theoretically, if you could travel backwards in time and all of these tickets allowed you to travel backwards in time, that would work as well. The cost technically would be the same. But I think it just makes more sense to just populate this thing from right to left in reverse order because then the code is going to be very similar to what we had before. Some people don't like it when I do that. If you really want to do it the other way, go ahead. But for an arbitrary value, suppose we're looking at this one in the middle. I want to know what's the minimum cost from here to travel along all these days. Well, it's going to be 3 different choices, right? It's going to be either I buy this ticket or this ticket or this ticket. And if I buy one of those tickets, then the sub problem is going to be, suppose I bought like the 7-day ticket from here. Then I could travel this day and this day, but I wouldn't be able to travel this day. So I would say that with the 7-day ticket, it's going to be a cost of 7 plus dp at this index, which is index 5. But I'll call that my index j. And so that is our current value dp of I. And we're trying to minimize this. So this is just one choice. There would have been the other choices as well. And we just want to minimize it. So that's pretty much what we're going to do. We're going to have one extra value in this array because imagine we did something like this. From here, we bought the 30-day pass. Well, I'll say I travel this day, and this day. So now I'm going to say, okay, what's dp of j? Well, j is over here. It's technically out of bounds. Well, we want to say that that's like our base case. We could say the cost is 0. So we're going to fix a 0 there. We're never going to remove that 0. That 0 is very important. It acts as our base case. So very quickly to do a dry run now, I'm here. I could do the 1-day pass, which will be 2 plus the subproblem here. That's going to be 4. I could do the 7-day pass, but 7 is already more. I could do the 30-day pass, but that's already more than what we have. So 4 is the value here. Once again, I could do the 1-day pass, which is 2 plus this, which is 6. Or I could do the 7-day pass, that's already more. And 30-day, that's already more. So I stick with the 1-day pass. Now, from here, once again, I believe we are going to do the 1-day pass again, because if I do that, I'll be 2 plus this, which is 6. If I were to do the 7-day pass, it would be 7. That would give me these days to travel. And then this would be the subproblem. So 2 plus 7, that's going to be 9. That's bigger than what we have here. And the 30-day pass, obviously, for $15 is going to be more as well. So 8 is the minimum value we can have over here. And here, there's probably going to be a tie because I think... No, actually, this is the first time the 7-day pass will be useful because if I do the 1-day pass, that'll be 2 plus 8, that's going to be 10. Or I could do the 7-day pass, which is going to be 7 plus I can travel these days. And then this is the subproblem, so 2 plus 7. That's actually 9, so that's less than what we had before. Once again, I could do the 1 day pass plus this. That's going to be 2 plus 9. That's 11. Or I could do the 7 day pass, which would give me these days, plus 4. 7 plus 4 is the same as we had, so there's a tie there as well. 11 is the minimum value. The 30-day pass wouldn't have worked. That's why I didn't really show it, but our algorithm would have tried that regardless. And then once we're done with all of this, we are going to return the value at the beginning of our array, because that tells us that starting from here and going through everything else, what's the minimum cost? It's 11. There's actually multiple ways to do this bottom-up dynamic programming solution. If we wanted to, we could actually have created an array of length 365. It would have been sort of sparsely populated. There would have been some zeros in there. Just imagine sort of like if the input was sort of like that as well. It was of length 365, and maybe there was just a 1 in the positions for the days that we actually wanted to travel and a 0 for the ones that we didn't want to travel. But anyways, I'm just mentioning this because I know somebody in the comments is going to say, hey, there's a different way to code this up. I know that there is, but the big O runtime doesn't really change. Knowing all of that, we can very easily translate this to a bottom-up solution. I'm just going to kind of take the concept that we have here, and I could have made an array. I could also use a dictionary. I'm going to use an array just because that's what I showed in the drawing explanation. So here it will be of length of the input array. So it's going to be all zeros, length of input array plus 1, because we want the last value to stay 0. And then we're going to go in reverse order. Python makes that pretty easy to do. So I'm going to say I in range. From left to right, it would be length of days. If I want to go through that range in reverse order, I can just put a reversed call around that. And I'm just mainly going to be copying what I have up above. Now I'm going to try to solve this subproblem. I'm going to take my j and I'm going to affix it. And I'm going to take dp of I, and I'm going to initially set it to infinity. We're trying to minimize it. I'm going to just literally take this loop here. I could type it out for you, but I don't know if that would make the explanation better, so I'll just copy and paste it. It's the exact same. And now for this subproblem, choosing this particular ticket with this duration, we want to try to minimize it just as we did before. So we want to figure out which day we land on. So literally just copy and pasting once again. And then once j stops, we will do the same thing that we did over here. So again, copy and pasting it. The only difference is now we don't have the overhead of the recursion. We already stored that value. We know it's already stored. And so we can just say dp of j like this. That's pretty much it. I might have a bug. I'm not 100% sure, but I know we're going to be returning dp of 0 once all of that's done. Let me get rid of the code up here. So now we can actually run this, but actually in case somebody wanted to see both of them side by side, here you can see this is the bottom up solution. This is the top down. They're very, very similar. I'm going to delete this now and give this a run. And yeah, you can see that this works. It is pretty efficient. When I ran it a few minutes ago, it actually gave me 80%. So this is a linear time solution and linear memory as well. If you found this helpful, check out Leetcode.io for a lot more. And hopefully I'll see you pretty soon.